Today you picked up the pink tables. So I'm going to be referring to those tables today. The top of those tables say that it is the standard normal distribution table. One of the sides is where the values in the table are positive, and one of them is where the z-scores are negative. So if you look at the top, it'll say positive, negative, but also look at the sides. The z-scores that are going down the table are either positive or negative. So we're going to be referring to that table as we go through and learn how to actually find the area underneath the curves that we were dealing with. You don't need your computer today, but I would get your calculator, something to calculate with. Yes. That is going to be yours, so you can do whatever you want. I would honestly not write on it. It is a table you're going to use over and over and over again, so like you can maybe write notes to yourself, but don't like circle or highlight or star any numbers. You'll get annoyed with yourself later. Does that make sense? Okay. So why do you have this table? So glad you asked. Last class we talked about how any normal curve, we can use the empirical rule if we know that it's normal or it has been standardized. So today we're going to work on actually doing the standardization so we can do this table and find the area underneath the curve since we don't know calculus to do it by hand. We use what are called z-scores. We talked about z-scores before. To help find the area underneath the curve by hand, the z-score allows us to transform a random variable x with a mean of mu and a standard deviation of theta into the specific random variable z that has a mu of 0 and a standard deviation of 1. So how do we transform these numbers? That is something that we learned in, I forgot what section, in chapter 3. These are the z-scores. You will do the random variable value minus the mean, all divided by the standard deviation. That would allow us to work not with the random variable x, but instead working with the random variable z, which is your standard normal distribution. And this z value is what is going to be in the table and allow us to find the area underneath the curves and apply it towards our x values instead of the z values. If a normal random variable x has a mean different from 0 or a standard deviation different from 1, like I said, x can be transformed into a standard normal random variable z whose mean is 0 and standard deviation is 1. Once that normal random variable has been transformed, that's when we're going to use that pink table, the standard normal distribution table, to find the area to the left. Now I want you to make a big deal out of it that this is to the left. When you're looking at the table, this is always going to be to the left of the value that you are looking for in the table. So the z-score and then the area value in the table is always to the left. It's kind of like you see in the image here. So if I'm looking at a particular z-score on that table, the number it tells me for the area will be the area to the left of that z-score. If we're asked, though, to find the area to the right, we can use the complement rule, which is 1 minus that number. I'm just going to put that right here for lack of better terms. 1 minus that number, that area, to determine the area to the right. Since the area would be found to the left, 1 minus would give me the area to the right. So it all comes down to the z-tables. We had an example last time that talked about IQ scores, and we were saying IQ scores can be modeled by a normal distribution with a mean of 100 and a standard deviation of 15. So an individual whose IQ is 180, if we calculate their z-scores, we would do 120 minus mu divided by sigma. So we take the value we're asking about in the question, you're welcome, 120, subtract mu, divide by sigma. And in your calculators, will you do that real fast? What is 120 minus 100 divided by 15? 1.333. And for standard deviations, we usually use 2 decimals, FYI. So we know that the z-score, that's what that's called, for this individual is 1.33. Their score is 1.33 standard deviations above the mean. So we can draw some conclusions here that the area underneath the standard normal curve to the left of 1.33 is. Now we need to look at our table for this. It is almost nearly impossible for me to show you this table because of the way that it is. So I need you to listen to my instructions since I can't show you what I'm doing. I need you to look at the table, and we got to find the number 1.33 on this table. So should I be looking at the positive side or the negative side? Positive. So I'm looking at the positive side. I'm going to go down the side that says Z, and it's going to give me the ones place and the tenths place. So I'm going to go look and find 1.3. The column that I want to use are all labeled by the hundredths position. So if you go over to where the 1.3 and the 0.03 meet, what number is right there? 0.90824. Boom. That number from this table that we just found. Does everybody follow? I know I can't show you it. That number, 0.90824, is the area underneath the standard normal curve, bless you, to the left of this z-score. Therefore, the area under the normal curve representing IQ scores that has not been normalized is the same. So even though this is really only for when the mu is 0 and the standard deviation is 1, we can apply it to our situation because it's been normalized. If we were trying to find the area to the right of 1.33, we keep the same number because my z-score did not change, but we're going to do 1 minus 0.90824, which is should be 808,176? Question mark? So this makes sense because these add to 1. That would be the area underneath the whole curve. Did I do that wrong? I don't have a calculator next. Oh, I do have a calculator next to me. 1 minus 0.908176. Yep. Wait. 0.091824 is what you guys got? Oh my gosh, I typed that number wrong. 1 minus 0.90824. Come on, Miss Quigley. Yeah, it's a 9. My bad. Okay, so boom, that's the area to the right of this value. So these eventually allow us to make conclusions about how good, how outlier, how unusual, if you will, our particular data point is. So let's see one from start to finish, okay, because that was example 0, had a lot of training wheels on it. Here's what an example or a question might look like. A pediatrician obtains the heights of her 3-year-old female patients. The heights are approximately normally distributed with mean of 38.2 inches and standard deviation of 3.17 inches. Use the normal model to determine the proportion of the 3-year-old females that have a height less than 35 inches. Here are the things I know. I know that the mean is 38.72 inches. That means right in the middle of this normal curve would be 38.72. I also know that my first standard deviation above and below that mean, if I add and subtract 3.17 from that number, would be 35.55 below, that's one standard deviation below, and 41.89 for my one standard deviation above. That creates my points of inflection. Those are important values on the normal curve itself. Well, obviously, this curve is not the numbers we have on our tables, and we don't have the calculus skills yet to be able to do this by hand, meaning not in my class, but eventually you might learn them. We're going to try to find the proportion of the 3-year-old females that have a height less than 35 inches. So I'm going to come in here, and at 35, I'm going to switch colors just so you can see that this is different. And here, I want to see how many of these females, or the area of the curve, that is less than 35 inches. Since I found less than 35 inches, am I talking about going to the left or to the right of 35? To the left. That's good. That means this is an easy one. The work you would show me here is as follows. We need to calculate the z-score for the random variable of 35. So we're going to do the random variable x, so 35, minus mu, 38.72, all divided by sigma, 3.17. what is the z-score for the random variable 35? Negative 1.17, I believe.
Yeah.
Confirmed? Okay, cool. So we have a z-score. The conclusions that we draw, knowing that we can now normalize this to a graph that does not have a mu of 38.72, it has a mu of 0 and a standard deviation of 1, that means we can draw the following conclusions. The probability that x would be less than or equal to 35 would be the area underneath the curve given that the z-score is equal to negative 1.17. So we can assume that our probability for our unstandardized curve is the area from the standardized curve. We take that z-score number and we find it on our table. So we're going to use the side of our table with negative numbers because the z-score is negative. If we're doing negative 1.17, you find negative 1.1 on the left side and then 0.7 at the top, and you find where those two numbers meet. Where do those two numbers meet? 0.12100. Do you agree?
Yeah.
Therefore, since that's the area to the left of 35 for this model, that normal model indicates that the proportion of the pediatrician's 3-year-old females who are less than 35 inches is 0.12100 or 12%. We can use the standardized normal curve to apply it to other curves that are normal but not standardized. Again, if it's just to the left, that's easy. Find the z-score, look up the z-score. That's the area, that's the probability. Area is the probability, area is the proportion. That's what we learned last class. Of course, it won't always be that simple, because what if the question is like example 2, and it asks you this time for the pediatrician, find the probability that a randomly selected 3-year-old girl is between 35 and 40 inches tall. So if I was just drawing this image, let's say this is the 35 mark, and then this is 40. I want to know this. So we have to get creative. Okay, we still have our, I can't help myself. We still have our mu of 38.72. Okay, so question, and that 40 looks atrocious. Let me try writing that again. So let's see here. What could we do with the math that we know to find this area underneath this curve? Now remember, your z-table always tells you to the left of a value. So if I were to find the area to the left of 40, it would include all of this. If I was to find the area to the left of 35, it would be all of this. Oh wait, I don't want that, right? Mathematically, what can I do if I have a way to find all of this and a way to find this little bit to get the middle section? I have a way to find this. I have a way to find this. How can I find just this? Say again? Okay, left of 40, right of 35. Left of 40 would give me all of this, and right of 35 would give me all of that. It's a good idea.
So you subtract the two.
So we could find what's to the left of 40 and take away what's to the left of 35, and I'd only have that middle part left, correct? So our goal here is to find the probability that we are between 35, and I'm leaving a space on purpose, and 40. 42, no? The question is asking for 40 or 42? Oh, it's asking for both. Let's pretend this is 40 because that's how I worked the problem out on my notes. So sorry. That's a typo. We'll go 42. Yikes. Okay. So that means that what you guys told me is we're going to find the area for a particular z-score. Miss Quigley. And we're going to subtract the area for a different particular z-score. That's what we need. Because if we find the z-score for 42, we can subtract the z-score area for the z-score of 35, and we can get our probability or our area. So let's figure out what those z-scores are. That first z-score, when x is equal to 35, we're just going to call that z sub 1. So this is our first z. I wouldn't put 35 down there because that's a different notation in this unit. We will do 35 minus the mu, which from the last problem was 38.72, divided by sigma, which is 3.17. 35 minus 38.72 over 3.17. Yeah, we found this in the last problem. Our second z-score for our higher boundary, we would do 42 minus 38.72 over 3.17. We calculate, what do we get? 0.39, right? What did I do yesterday? What'd you get? 1.0. Yeah, same. Yikes, I don't know what I was doing. Okay, my notes are all over the place. Okay, so this is the z-scores that we have. Now we're going to take the z-score for the 42, which was that 1.03, and we're going to subtract the area gotten by the z-score of 1.17. So we look at our table twice to get these values, and I'm going to scoot my numbers over. For 1.03, we go to the positive side, we go to 1.0, and then 0.3, what number is there? 0.84849. And we're going to subtract the area to the left of 35, which was the z-score of negative 1.17, which we found in the last problem to be 12100. And when we subtract those numbers, what do we get? So the normal model indicates that the probability a randomly selected 3-year-old female is between 35 and 40 inches is this 0.72749 or 72.7%. So if we randomly selected 100 3-year-old females, how many would we expect to be between these two values? Somewhere between 72 and 73, right? We'd assume this many would be between 35 and 40 inches tall. Now that's a lot. Remember, we're getting 100 kids and we think almost 2/3, 3/4 of them. But look at how much of this graph we've colored in. So that's a reasonable conclusion. So as a bit of a summary, we've already seen a couple examples, one where we just took something to the left. A little bit earlier, we did a cute example to the right. Now we've seen one in between two values. These processes are summarized in this table here with a visual. So if you're asked to find the area to the left of a value, you're going to convert the value to a z-score and use that pink table to find the row and column for that area. If you're doing it to the right, you're going to convert the x to a z-score. Go back to use the table, but since we're going to the right, you're going to do 1 minus that number. And if we have an area between two values, you find the z-scores for both and subtract their areas, the bigger one minus the smaller one. Sound good? Cool. That's the big conclusion for today. Let's see a few more examples. Often, we do not want to find the proportion, probability, or percentile, which is what we were just doing, given a value of a normal random variable. Rather, we would want to find the value of a normal random variable that corresponds to a certain proportion, probability, or percentile. So we're going to be solving for something different here. We're back to our pediatrician's example. The heights of the pediatrician's 3-year-old females are approximately normal distributed with mean 38.72, standard deviation 3.17, same vibe. Find the height of a 3-year-old female at the 20th percentile. What they've given you is that you actually have this area here. I guess I should use purple since that's what I was using. You have this area for a particular x value, and the area right here is 0.2 for the 20th percentile. Because that's the proportion of the population, that's the probability. These percentiles all work together under this normal curve. So if we have the area, we need to find the z-score that gets us closest to that area. So we would do the following work. I would say the area that z is equal to some number will be equal to 0.2. We were given the area, which means we were given the number in this table. Not the number on the side and top, but the number in the inside of this table. On a scavenger hunt with your pink paper, can we find the number 0.2 in your table? Just 0.2. You're not going to find it exactly, but I want you to find as close as possible to straight up 0.2. No. No. So this one, again, you have the area. You're looking in the insides. Scavenger hunting through the insides to find 0.2. That's a good question. Scavenger hunt for it. Which side has 0.2 in the bulk of the table? It's a scavenger hunt. Now you can get closer. So somewhere between, so if you're looking, yes, find negative 0.8. Do you see how it goes from 0.20045 to 0.19766 between 0.84 and 0.85? Yeah. So what's a little bit in between 0.84 and 0.85? This is going to be negative 0.845. So we scavenger hunt. If we're given the arrow, we have to scavenger hunt this thing to find the z-score. We just found the z-score. After lunch, I'm going to tell you what to do with that z-score to answer this question. So now that we have this z-score, we're trying to find the x value that would get us this z-score. So we're going to take the formula for z-scores, which in case it's written on only the other side of your paper, it's z equal to x minus mu over sigma. We're going to plug in what we know, which means we know the z-score is negative 0.845. We know the mu for this equation is 38.72. We know sigma is 3.17, which means we can solve for the x. We can solve for the height of a 3-year-old female at that 20th percentile. If we were solving for x, what would we do? Well, how do we get rid of this first? Multiply it. So, and I'm not going to actually multiply any numbers to the very end so that I don't round a number too soon. But we're going to multiply 3.17 onto both sides. That'll be equal to x minus 38.72. One more again. How do we get the x all the way by itself? Add 38.72 to both sides, which means in our calculators, we're going to do negative 0.845 multiplied by 3.17 plus 38.72 and figure out what that x value is equal to. What did y'all get? 36.04 inches. So if a 3-year-old female was 34.04 inches tall, she would be in the 20th percentile. Bonus points, what does it mean to be in the 20th percentile?
It means 80% of the people, yeah, did better.
80% of the people did better than you. Or in this case, are taller. Because we're measuring height. Example 4 is going to ask us to find the value of a normal random variable. Same thing. It says scores earned on the mathematics portions of the SAT, the college entrance exam, are approximately normally distributed with a mean of 516 and a standard deviation of 116. What scores separate the middle 90% of test takers from the bottom and top 5%? In other words, find the 5th and the 95th percentile scores. So if we were doing this again and I'm trying to draw on my curve, that means I want to know what numbers are here and here. We'll call them x1 and x2 because we can see that bottom 5% and the top 95%. Now here's what we know. We know that this area is 5% or 0.05. We also know that this area is 5% or 0.05. So if we start to try to do what we did in the problem above and finding the z-scores that best gives me the area of 0.05, we would set up something like this. We would say, all right, we're going to have to do this twice. So we want the area where z is equal to some number to be 0.05. That would give me the area to the left here being 5%. My question for you is, because we'll go to our table and we'll do that scavenger hunt here in a second. If I'm setting up this other side, what number would I make this equal to?
1 minus.
Well, question, this table, what we're finding the area is always to the left. So if this is 5%, what's to the left of it? 95%. So we're actually finding this number on our table because it would separate the top 5% since that 5% is on the right. Scavenger hunt time. Yes. I'm sorry, say that one more time. We are. We don't know the z-score that gives us this area. So your table has all the areas in the bulk of it. And so we're trying to find 0.05 so then we know the z-score. Yeah. Okay, so scavenger hunt, 0.05.
-1.6. And 0.0.
What? And 0.0 what? Look. So if I'm looking for 0.05, I'm looking for the smallest 0.05, and I see one that says 0.05050, and the next one says 0.04947. So I probably want the number in between those two, yeah? That is row -1.6, and in between column 0.04 and 0.05, which means this number would probably be -1.645. It actually is. So if we go look at the other side, 0.95, the z-score that gives me that one is in the same spot, but it's positive 1.645. Now, of course, now we have the z-scores. We need the x values that would have given us that z-score. So we're working backwards. So we're filling out the formula for the first x value, which would be 0.05 equal to that first x value minus 38. Nope, that's the wrong number. What's the mean? 516 divided by 116. And then we would have 1 point, that's wrong. I put the wrong number right here. Why didn't you stop me when I did something silly? 1.645 equal to the second x value minus 516 over 116. You don't have to show me the work here if you know how to solve this. The steps are going to be the same as we did them up here when we're solving for the x value. What did we do first here? And then what did we do next? Add or subtract. Okay, so that's what we're going to do here. So we're going to do negative 1.645 times 116 plus 516 to get the first x. What's up? So you can do this algebra, not in your head because you're probably doing it in a calculator, but multiply by this. And then add this to solve for x1. If you solve for this first x, you would get 325.18. And if you solve for the second one, you would get 706.82. So our conclusion is this. SAT mathematics score that separate the middle 90% of the scores from the bottom and top 5% are 325 and 707. SAT scores are not rounded to decimals, so we rounded it to its nearest whole number. Put another way, a student who scores 325 on the SAT math exam is in the 5th percentile. A student who scores 707 on the math SAT is in the 95th percentile. Because we're looking at the bottom and the top 5%, this will allow us to identify scores that are unusual, because unusual is 5%, yes? So it does eventually help us go back to that question of, is this an unusual result? The other thing you're going to see is a notation, and I'll be honest, I don't think I ever saw this notation outside of this textbook, like when I studied stats before. Doesn't mean it's not real and that I just didn't see it. This notation, z sub alpha, so let's highlight that so you can see that it is a z with a subscript of alpha, so we pronounce it z sub alpha, is the z-score such that the area underneath the standard normal curve to the right of z sub alpha is alpha. So it's actually giving you the area as that subscript and asking you to scavenger hunt and find the value. Also, please underline the words to the right, because our table, bless you, our table, does it give you to the right or to the left? Look at the picture. Is that area to the right or to the left? To the left, so that's very important for us to notice. So if the question asks you to find z sub 0.1, that means that we can quickly come over here and do 1 minus alpha to see what value we're looking for. This would be 1 minus 0.10, which for this problem, 0.9. So we are looking on our table for the area of 0.9. So scavenger hunt through your document, try to find the closest thing to 0.9. Basically, we're looking for where it changes from 0.89 to 0.90. Where would that be? So how would we write that number? If it's in between those two columns, in between 0.08 and 0.09, 0.285. So it's basically like a quick little scavenger hunt question, but since that alpha value is to the right, you do need to make sure you do 1 minus to use your table, because your table is all to the left.